Thank you so much for inviting me to this conference. This is actually the first time I'm speaking to a room full of lawyers, so it'll be interesting. We'll see. I'm a physicist, so we'll see how it goes. I am married to a lawyer, so I kind of know a little bit about the profession. Okay, so I wanted to talk about two capabilities that have long been thought to lie at the apex of human intellectual development. That is creativity, as exemplified by this beautiful Salvador Dali painting, human Dali. We'll talk about the AI Dali soon. And then reasoning. For example, the mathematician Andrew Wiles finding a proof for Fermat's last theorem. Of course, the legal profession requires creativity and reasoning in spades. And at least at my understanding, I think there are apt analogies between writing a precise mathematical proof and constructing a precise ironclad legal argument, right? There's also creativity in getting around the law, I suppose, as well, in a legal way. Okay, anyways, but so okay, there are sparks of these capabilities inside machines as well now, right? So there's the AI DALI, which can create seemingly endless amounts of creative images through these diffusion models. And these diffusion models can not only creatively create new images, but they can also create new proteins, new drugs, new robot policies, new types of language as well, right? So where is this creativity coming from? How does it work? How do we regulate it? How do we drive policy from it? What implications are there for copyright law and so forth? On the reasoning side, we've recently, as a community, made incredible advances in reasoning to the point where AI systems can now solve, for example, international mathematical Olympiad problems to the level of almost obtaining a gold medal, right? This is incredibly difficult. It's like a very tiny percentage of the human population can achieve a gold medal. I don't think I can, or at least I couldn't when I was a student. I probably still can't, honestly. So, so it's remarkable. What's going on here? What implications does it have? How can we co-opt these ideas from mathematics and infuse them into the legal world? I think creativity and reasoning, the quantum leaps that we've achieved in AI, will be seeping into law somehow, though the precise form factor is unclear at the moment. We've made some progress in really understanding these things, and that's what I wanted to talk about. So I'll just talk about two things. First, how do diffusion models actually generate new images that are very different from the training data that they've seen? And reasoning, how does that actually work, and how can we improve it? Okay, so let's start with creativity. And if you're interested in the technical details, it's all in this paper by an excellent graduate student, Mason Kam, who worked on this. Okay, so again, the question is, where do these images come from? Where does this endless creativity come from? So the first diffusion model was actually created in my lab many years ago by another excellent postdoc, Joshua Soldikstein, who's now at Anthropic. And the ideas actually came from physics. And so to explain the origins of creativity, I need to say a little bit about how diffusion models work. And of course, understanding how these technologies work is, I think, incredibly important for deciding deciding policy for how these systems interact with society. Okay, so how do these systems work? Well, they're trained to reverse diffusion. So what is diffusion? You take an image, a training set image, and you just add noise to it. You let the pixels diffuse and become noise. So then eventually, as you add more and more noise, you just get a white noise image. Okay? And then you train a neural network to reverse this diffusion process. So you train the neural network on these trajectories that undergo the reverse process. And if it works, then if you start from noise, you feed it through your neural network, you'll generate hopefully a new image. Okay? So that's the basic idea, but this raises a puzzle. That puzzle is you only have a finite training set, right? So if you perfectly reverse this diffusion process, why would you generate anything other than a training set image? How could you possibly generate something far from your training data, right? So if you're reversing, going from noise to a training set image, at test time, when you use the model for new pieces of noise, why do you go to anything else? Okay, this was a puzzle that's been raised in the field. It's a well-known puzzle. Basically, if a trained diffusion model succeeds in reversing diffusion, then it should fully succeeds, and it should only be able to generate sample training points. It cannot be creative and generate new samples far from the training data. So then the creativity of diffusion models must lie in their failure to perfectly reverse the diffusion process. But how can diffusion models fail in intelligent ways that still generate creative but sensible samples? Okay, so that's the puzzle. There's a mathematical formulation of this puzzle and so forth, but I'm skipping all those details, of course. We recently solved this puzzle, okay? The key idea is that the neural networks that are trained to reverse the flow of time in the forward diffusion process aren't infinitely powerful for good reasons. They have a local structure. So for example, there are these convolutional neural networks where you feed in an image and then the output tells you which direction the image should flow to reverse the diffusion process. This neural network is local, which means that the decision that any pixel here makes to go backwards in time only depends on its local neighbors, okay? And this neural network is equivariant, which means the decisions a pixel makes here, depending on its local neighbors, is the same decision rule that a pixel here follows depending on its neighbors. So different parts of the image are all doing the same thing, and they're not paying attention to other parts of the image as they're reverse flowing. So that means that each local patch alone becomes close to some local patch of the training image, but different patches can then go to different training image patches. And global consistency arises from overlaps between the patches. And so then creativity arises from mixing and matching different training example patches in different locations. Now, I've explained this in words, but it's important to state that there's a quantitative theory behind all of this in the form of differential equations that you can just write down. Okay? So just to explain the same idea in pictures, if you had a neural network that could perfectly reverse diffusion, the entire image would flow backwards in time and flow to one of the training set images. So here's a stack of training set images. Depending on what the initial noise is, it would flow to one of them and nowhere else in image space. The local equivariant reverse diffusion, what it does is one local patch will flow to some training set image local patch, and another local patch will flow to some other training set image local patch, and so on. And you get this local patch mosaic, okay? So how good does our theory work in explaining what diffusion models do? It turns out it works remarkably well. So here's a theory experiment comparison, okay? So what you're seeing here is you're seeing pairs of images for different training sets and different architectures. The right pair is the image that's spit out by a trained diffusion model, right? You pick some random noise, you feed it to your trained diffusion model, you get an image, right? The left image is our theoretical prediction of what the trained diffusion model would spit out without actually training any model whatsoever, right? For the same noise input. So you can see there's a beautiful match between theory and experiment across a bunch of examples. There's many more in the paper. And the match is quite quantitatively high. So we really have a good theory of what these diffusion models are doing. And they're essentially achieving exponential creativity through this local patch mosaic model, okay? Now you can ask a very basic example that's relevant to law, is when will these diffusion models actually be creative and when will they copy their training data, okay? And there was some earlier experimental work that was looking into this that was quite instructive actually. So what you do is you train two different diffusion models, model 1 and model 2, on two disjoint subsets of the data. So model 1 is trained on one subset of the data, in this case faces, and model 2 is trained on a completely disjoint subset of the data, a different set of faces. And then you slowly increase the amount of training data, right? So obviously if you only have one training image, the model copies that training image, right? So okay, so here's the image generated by the model, and here's the closest image in the training set, and you can see they're basically identical. So the model is creating or copying a training set image. This persists even if you go up to 1,000 images in the training set, right? Especially at 100, you can clearly see it. So here's an image generated from model 1, and here's the closest training set image, and you can see it's just copying it. Here, it's also copying it, but it generates a different image from, model 2 generates a different image from model 1 because the training set is disjoint, right? So here, model 2 is generating a sample, and here's the closest image in the training set, and it's clearly a copy. But something remarkable happens, a phase transition happens, if you increase the amount of data by a lot. Then what happens is, the two models start generating new samples, new creative samples that are not close to the training set. For example, this generated image is not like the closest training set image. This generated image is not like it's the closest training set image. But remarkably, the two generated samples are identical. So these are two different diffusion models that have converged to the same model, and that model is creative, right? So this suggests that there's a very complicated, there's actually a simple but nuanced landscape of what these diffusion models do. So physicists would call this a phase diagram, right? So you have one axis that tells you how powerful is your diffusion model, what's its expressive capacity, roughly how big is it, how many parameters does it have, okay? The other axis is how much data do you use to train it with, okay? And there's a phase boundary here where for a given complex diffusion model, if you don't train it on too much data, it's just going to copy its training data. But if you train it on enough data, it'll suddenly not copy its training data and become creative. And different models will converge to the same creative model, right? In some sense, our work was inspired by this, where we were asking, what is the model that it converges to? And it converges to this patch mosaic model of creativity. Okay. So just to summarize, so we've developed the first analytic theory of creativity in diffusion models that can quantitatively predict new samples and precisely explain how they're composed out of their training data. These diffusion models combine different training set patches at different locations of the image, and they can construct exponentially many new samples through this local patch mosaic model of creativity. There's much more to do here because we looked at simple diffusion models that are only convolutional. More complex diffusion models that generate more complex images have transformer layers in them. Transformer layers break locality, so we don't yet have a theory for what they're doing. We're working on that. Okay? But this suggests that like having a deep understanding, a theoretical understanding, not just an applied machine learning understanding, but a theoretical understanding, you can start to imagine how this might inform copyright law and policymaking and so forth. Okay, reasoning. How does it work and how do we improve it? All right, so we're all used to large language models, so that's this little box here, right? So I'm hiding a lot in that box, but the basic idea is you train a neural network to take a large chunk of text and predict the next word at internet scale, right? That's what these language models do. They're literally next word predictors. What's been shocking is that next word prediction alone, as a training objective, can unlock so many emergent capabilities, okay? But they're still not powerful enough to do deep logical reasoning. Because if you just predict one word at a time, you can quickly go off the rails and start spouting nonsense, okay? So how do you get this reasoning, like these alpha geometry and alpha proof that can win mathematical Olympiad competitions? You start coupling the large language models with auxiliary agents, so to speak. For example, a proof assistant verifier. And so this language model is trained not only in English, but it's also trained on large corpora of math. So it's pretty good at, or somewhat good at guessing, say if you give it a theorem and say, I want a proof, or maybe eventually in law, if you give it a goal, it might give you a legal argument to prove that goal. They're pretty good at guessing one step, but they're not perfect. So what the proof assistant verifier does is it takes the guess of the next step or tactic in a proof, and it just checks, is it correct or is it not correct? This can be done using formal models of mathematics known as lean. Lean is a formalization that makes, it's basically like a software code for, it's like a code for writing math proofs. So this is like a compiler for that code. It can check whether the code is correct. And so this is what the proof assistant verifier does. Then the proof assistant verifier returns to the large language model whether its guess is correct or incorrect given the current goals or given the current theorem. So then if it's incorrect, the large language model can backtrack or maybe even start over. If it's correct, it can guess the next step. So then this loop between the large language model and the verifier effectively boils down to a search process where you start with the theorem, you guess a particular tactic. If it's legal, you keep guessing until you hit some time limit. If you don't find a proof, you start over, and you might make different guesses, and then end up at a correct proof. So this is basically search now. It's actually interesting, at a 30,000-foot level, the field of AI has two major games in town. One is learning, adjusting the weights of a neural network to solve a problem. And one is search, just brute force searching a huge space. The last decade has seen advances in scaling up learning. And search never really worked because our search spaces are so large, like the search space for mathematical proofs is so large, you can't do brute force search. What's made search possible now is the existence of better guessers through learning, right? So now, what's recently been happening, oh, and by the way, there's an analogy to this, to human reasoning, that people have made that's not unreasonable. You can think of your large language model that guesses the next step as the analog of what Kahneman, a psychologist Kahneman would call system one, or our fast intuition. We often guess next steps, and we don't really know where our guesses come from. They're probably coming from subconscious thought. But then you also have a slower system two that's deliberative deductive thought, right? That's very much conscious. And you can think of the proof assistant verifier as that. Okay, so now that we've been able to scale up search by exploiting a good learned guesser, this opens up an entirely new axis for scaling laws, which is how much compute do you allocate to search, right? So this horizontal axis is roughly how many times you search the search tree, and this vertical axis is performance, so the probability of being correct in whatever reasoning problem you're working on. And you can see that the probability of being correct goes up smoothly with the number of samples, but it's a quite slow rise. It's actually logarithmic in many cases. But in any case, this provides a convenient axis for achieving improvement. This is what OpenAI means when they say if we let our models think more, they do better. Okay? All right. So this is quite interesting now that we've gotten learning and search to work, but can we make them work better together, right? So we've had these two phases that haven't yet talked to each other, right? The large language model is just trained to do next token prediction or next word prediction. And the search is trying to take multiple parallel guesses along a search tree, okay? But they satisfy conflicting design considerations. The learning and the inference or search are not co-designed, and therefore they can be suboptimal. What is the dominant failure mode, okay? The dominant failure mode is that learning, by predicting the next word, it likes to place as much probability as possible on the most likely next word in the training set, okay? So it's very confident. It puts a lot of probability in a small set of next steps. This is fantastic if the next steps are correct, but it's terrible if the next steps are wrong. We've all experienced colleagues who are confident and wrong, right? And they're very difficult to work with. In fact, a Stanford professor who's confident and wrong can wreak a lot of havoc. And you've probably seen that in the past. That's why I try to stay unconfident, at least. Okay, so the way we train our LLMs tends to make them confident and wrong because we try to force them to greedily pick the most likely next word. If you have a guesser that's confident and wrong, then intuitively, no amount of parallel search will rescue the guesser, because the guesser will confidently say, go this way, this way, this way, and search can never then find good proofs that lie on lower probability choices that would rarely be made by the guesser. Search instead would like you to spread your probability across many promising steps. So let's say that I were to tell you, you got to solve this problem, but I'm going to give you 10,000 guesses, okay? Your guessing strategy would be different. You would like hedge your bets and say, I don't think option 24 is that correct, but I'm going to throw it out anyway because I get 10,000 tries, right? So search would like you to spread your probability across many promising steps. Learning likes to place all your probability on the most likely step. So learning can hurt search if learning and search are not aligned via co-design. So we actually showed that the learning can actually hurt search, and we found a solution to this problem. And this is great work done by 2 grad students in my lab. These appear to be mugshots of them on the web. But remind me to ask them for better pictures. Okay. We actually were able to prove a mathematical theorem that roughly says if you're allowed n searches at test time for small n, your learned guesser should confidently exploit. You don't have that many guesses, so put all your eggs in the one basket that you think is most likely. But if you're allowed n searches at test time for large n, you should unconfidently explore. You're allowed many guesses, so spread your probability around. We discovered an efficient algorithm that chooses the right amount of exploration for any amount of n searches at test time. And we got better performance. So what you're looking at here is the number of times you're allowed to search at test time on the horizontal axis, okay? The vertical axis is the performance of our combined guesser and verifier on finding mathematical proofs, okay? If we co-design the learning and search, so we change the learning algorithm for the different levels of search, we obtain this black curve up here. And if you don't do the co-design, if you just do learning the way everybody does it and then search the way everybody does it, you get this red curve here. So you get a substantial improvement by co-designing learning and search. And just the technical details, we trained an 8 billion parameter language model in math with different levels of exploration or search at test time. These are not solving mathematical Olympiad problems. These are much smaller models. But they can basically find proofs that are of the level of exercises that we would assign our graduate students in math in complicated subjects like algebraic geometry and so forth. And they can find these proofs. Okay? All right, let's zoom out a little bit. What do I think are the big future directions? So just like we found a theory of creativity, I would really like a theory of reasoning. Again, if you haven't noticed, I'm a theorist and a scientist primarily. I really like to understand how these systems work and then use that understanding to improve them. So I'd like a theory of these inference time scaling laws. How does performance scale with search as a function of the quality of the guesser, the difficulty of the search space, and the quality of the verifier? I think in the legal domain, interesting questions for you are how can you co-opt this machinery in the legal domain? What is the role of a verifier, an automatic verifier? What is the search space? How can you generate good guessers? What is application, actually? Then what's really exciting is a theory of recursive self-improvement. When and how fast can it work? And this, I think we're going to see a lot of performance gains coming forward from this situation, where basically you have the same loop that we've been talking about. A large language model guesses next steps, the proof assistant verifies them, and eventually you start finding new proofs. But then you can take these new proofs and you can feed them back to the large language model and do learning on its own self-generated proofs. So it trains on its own synthetic data, right? There's been a lot of work on training, say, diffusion models and other things on their own generated stuff. But quickly that degenerates because their own generated stuff is not that good. So if you train on your own bad things, you'll degenerate and start creating a bunch of nonsense or images that don't really look good. But here you're not just doing that. You have a verifier that's filtering your generations and doing quality control. So if you generate stuff and have a quality control mechanism to only train on the highest quality things, you can imagine recursive self-improvement where your capabilities exponentially run away. The AI safety community is actually quite worried about the possibility of recursive self-improvement. But to be honest, we haven't totally gotten it to work. And I would love to understand better conditions under which it works. I think there has to be a threshold of how good your guesser is and how good your verifier is before you can see recursive self-improvement. And I don't think we're at that threshold yet. We'd like to understand where that threshold sits for various models. Okay, but zooming out, so zooming out, and this is my last slide. I think there's a much longer term future in bridging biological and artificial intelligence. A part of the work that I do is also neuroscience and understanding biological intelligence. And I recently gave a TED AI talk on this where I think there's actually many areas where AI is orders of magnitude worse than human intelligence. And there's huge order of magnitude gaps to bridge. And so if you're interested, you can find this talk on the web where I talk about data efficiency. Current language models are trained on order 1 to 10 trillion words. We as humans get 100 million words. It would take us 24,000 years to read 1 trillion words. So we're much more data efficient than LLMs, large language models. We're much more energy efficient. Our brain only spends 20 watts. Large language models, when they train, can spend megawatts, right? So we're orders of magnitude more energy efficient. We can go beyond evolution to co-opt biologically inspired algorithms, but implement them on quantum hardware. I'm working on that with my colleagues in the applied physics department. Explainability, we really don't understand how these machines work. We need better explainable AI to really understand what we're doing, and I'm a firm believer in understanding leading to more informed policy. And then melding minds and machines. We can actually create bidirectional communication between AIs and brains. And in mice, for example, with Carl Dijkstra here at Stanford, we were able to build a loop between brains and machines and actually write in patterns of activity into a mouse brain to get it to imagine certain objects. Anyways, so this is a completely disjoint talk, but if you're interested, you can find this easily on the web. Okay, I'll stop here. Thanks.
It's mystifying enough. I understand neural networks to the extent that I can, and those are old, and we were taught about dynamic programming and neural networks decades ago. And turning an image into noise and then reversing that process and coming out with a different dog, that's not explained very well there, I don't think. But
yeah.
The more mystifying thing is your verifier.
Yeah.
I sort of know what's happening in a neural network, but then you have this little box that says, I'm checking you.
Yeah.
Why don't we just use that thing?
Because it's only good at checking. It's not good at searching on its own, right? So when
is there a high-level answer or understanding for how does it check?
So there's many examples where it's hard to find a solution but easy to check, right? So for example,
cryptography.
Yeah, exactly. It's like that. Proof finding is hard, but checking if a proof is correct is easy. You just check if each deductive step is valid, right? But you don't know ahead of time which deductive steps to use. Yeah. Okay. By the way, this is the first theory of how you get these new images, and it was just a couple of months ago from my lab. So you're right that it's hard to understand. The first theory paper on this just came out a couple of months ago.